Hi, I'm Ben-Yaakov. This presentation is entitled Electrical Tingling Sensation with a Two-Prong Power Adapter. Let me first explain the problem. Suppose we have a laptop and there is an adapter that we plug into an outlet. It could be, say, a European type or a US type. US type could have a symmetrical contact, so one inch is a little bit longer, and we plug. This is a two-prong plug it in, and it turns out that in some laptops that do have a metal parts on the casing, when you touch it, you feel sort of a tingling sensation. It feels like sandpaper as you rub it over the metal part. Okay, so this presentation is going to discuss this problem and see what's the reason for it and how can one overcome it. So let me start off by just giving the actual reason for this sensation feeling, this tingling feeling, and that is that there is a current flowing from the AC line through some impedance, and then there is a capacitor in between through the person back through ground to the AC line. So this current is the reason for this tingling sensation. We're going to see what's the reason for this capacitance and where is it coming from. I think one of the first questions that comes into our mind would be, is this dangerous? Well, it turns out it's really not, because there are some safety standards that talk about touch current. Touch current is this current that will flow into your body when you touch the metal part of the casing. And there are actually two standards. One is a UL, one is an IC. And they are talking about a limit of 3 milliamp. That is a maximum of 3 milliamp that is allowed when you touch some electrical appliance or a laptop. Now, if we are talking about a capacitor and we are talking about a line frequency, let's just take an example. Suppose this capacitance is, say, 1 picofarad, the 50 is supposed to be hertz here. Then the current is omega C times V. V is 220 volts, the European line, and you calculated it to be 70 nanoamp. This will be for 1 picofarad. Now, if the capacitor is 1 nanofarad, 1,000 times larger, the current will be 70 microamp, way below the 3 milliamp. So these would be the kind of currents which are expected. So they are way below the 3 milliamp limit. So let's not worry about a danger here. In fact, if we look at the standards, this is the IEC threshold and the UL limits, the solid and broken lines. They are talking about a startle reaction. That is, as you touch something, you sort of pull your hand back, you feel like tingling. They're talking about 0.5 milliamp. This is in milliamp. These are frequencies, and as you can see, the sensation or the danger is higher at lower frequency than in higher frequency. And the reason is that at much higher frequencies, the current is actually passing through your skin and not penetrating. So at low frequency, it's sort of more dangerous if the current is high. So we have a limit here of 0.5 milliamp. This is the startle reaction. Let go is said that when you just would like to leave it alone, and this will be 5 milliamp. And then if you get to 20 milliamp, this is really the dangerous area where you can get a fibrillation, a heart attack, and this is really very dangerous. So these graphs are really not talking about this tingling sensation or this kind of sandpaper feeling as you rub your finger across the casing, which is much below the 0.4, I mean, you start feeling it much below the 0.5 milliamp. So let me start with the explanation, talking a little bit about the power line and its AC outlets. Now, the European is sort of symmetrical. In the US, the new code talks about a longer contact for the so-called neutral. We'll talk about it in a second. But in older houses, you'll find that these are actually symmetrical. Now, in the power line, we have the power station, the power generator, and then there's the power distribution system, which is high voltage lines spread it out. And then locally at the residence area or industry area, you'll have a local transformer, which is a step-down transformer bringing the voltage to, say, 110 or 220, depending on the area you are living in. And the point is that one side of this transformer is connected to ground. So this line is called the neutral. And the other line is the hot line. Now, there is a voltage between these two. It's an AC voltage, but this line referred to ground is almost zero. In fact, here it's like a ground potential, but here at the socket, at this pin, the voltage is not zero, it's not ground, because there's some current flowing in this line when you plug in something, and obviously there is a voltage drop along this line, so there is some potential here. But these are low voltages. We're talking about a few voltages, 2, 3, 5, as compared to, of course, to the 110 or 220 you'll have on the hot side. So this is the arrangement that is now used worldwide, as a matter of fact. Now, in the case of a three-prong electrical outlet, there is a third pin here, and this pin, however, is connected to ground, but locally, that is at the residence side, factory, industry side. That is, at the transformer, there is a connection to ground. This is the neutral. This is this line here. This is the hot side, but locally, it's also grounded. So the potential here is pretty close to the ground potential. As I've said before, this line or this pin is neutral, and normally there would be a voltage difference between this line and this line, because this is the local ground, this is connected to ground here, there is some voltage drop, so there is some difference. Again, it's small as compared to the line voltage. So this is the arrangement for a three-prong electrical outlet. Now, in the case of a three-prong connection, this ground is actually be connected to the casing, okay, of the, say, laptop or appliance or whatever. So this is now grounded locally, because this is now the local ground. Now, let me start a discussion of this current, this tingling sensation, by talking first about a sort of a older adapter, which is using a low frequency transformer. Here is the transformer, okay? So these are these bulky wall-mounted chargers or adapters. Here's the transformer. Here there's a connection. This is the plug now. This is the outlet, and this is the plug. This is the line. There is a distance here. And here is the neutral connection. Transformer. There's a secondary, which is a lower voltage, a rectifier, might be a regulator. And then we have the output voltage. Now, in a transformer, between the windings, there is some capacitance. Okay, I'm showing it here. This is the primary, this is the secondary, and here is the capacitance. It's the interwinding capacitance. Well, we can see it a little bit better here. This would be the core. For a low frequency, it will be a laminated magnetic core. And this is sort of a cross-section here, like cross-section here, and we see the winding. We see the primary, and this is the secondary, say, over it. This is the input AC, and this is the output. Now, since these are close together, there is some capacitance between them, like two plates, and some distance between them. And we can see it actually a little bit better here. Perhaps this is another cross section, and we see the primary. This is the red one. This is the secondary, and here is this plate of this capacitor in between the primary and secondary. So there's a capacitance here. So here what happens? We have the AC source, we have the plug, this is the transformer, output section. Now we have this capacitor in between the primary and secondary. And there is a connection here, and so if a person touches this casing, here it is. We're going to have a current flowing in this direction through the capacitor. Now, of all these, along this path, this branch, the capacitor has the highest impedance. So it'll be actually the limiting element of the current. And as we have seen before, if it is in the picofarad, 100th picofarad, we are expecting to see something in the area of, say, microamp current passing through here. Person standing on the floor. Obviously, if there's an excellent insulation, no connection to ground, person is sort of floating, then there'll be no current. But in reality, there is always some sort of a leakage here, whatever you do, and therefore there's this feeling of tingling when you touch this casing. If it is a metal casing, if it is plastic, of course you won't feel it because it's insulated. So if, however, we are using a 3-prong power adapter, and this ground, local ground, this is the local ground, this is the neutral, this is the local ground, is connected to the casing, then the current would go this way, not through the person. Well, the reason is that the impedance here, resistance, is much, much lower than through a person. This would be like few ohms, while through the person it would be like few kilo ohms, and obviously the current will find its way through the much lower impedance or resistance through here. So this is the idea of grounding a casing so that the potential will be ground potential and be practically no voltage between this area and ground. So when touching it, you won't feel anything. Now, interesting enough, in some cases, when you flip over the plug 180 degree, okay, I just exchange these two pins, you might say, you don't feel anymore the tingling. That is, before flipping it, you can, when touching the laptop, the metal part of the casing, you'll feel the tingling, and then when you flip it over, you don't feel it. Okay, so why is this? Well, the reason would be the way that the wires are actually wound across the core. Okay, so here we have the primary, here we have the secondary. Now we start winding, at the inner side, and then it goes up and up. And so the question is, what is inside? That is, this wire, which is buried inside, to which part of the line it's connected. Now, preferably, this should be the hot side, while on the outer side, it will be then the neutral side. So now you have a capacitance, but the capacitance is between the neutral and the secondary. Here we see it. Here, this is now the neutral side. This is the neutral side. The hot side is buried inside. And so we have between the neutral and the output, and therefore there's practically no potential difference. I mean, the voltage is very low, so the current will be low. Now, if you flip it over again, obviously you'll exchange this hot with this side with the neutral side, and you'll have the hot side outside, and then there is a potential difference, and there'll be a current. Okay, so in this case, when flipping it, if you can, in the US, when it's a non-symmetrical socket, you can't flip it. But if you can, then if you use a low frequency adapter and it is built this way, then one orientation you'll fill it and the other you won't. So what really happens here, that instead of having this capacitance, when it is flipped correctly, say, you'll have this capacitance, this is the neutral side, and therefore there'll be no current, or practically no current, because there is very little voltage difference between these two, potential difference between these two lines. So let me move now to the electronic adapter. The electronic adapter will typically have an input filter, a bridge rectifier, a switcher. Normally it'll be usually a flyback type converter, and then there is an output section with a rectifier and controller, maybe a regulator, and there's normally a feedback so that the output voltage will be maintained at the level that is required. Okay, so again we have the AC side, this is the neutral, connected directly to the adapter. There's no transformer here. There is a transformer here, but this is a high frequency transformer. Now when the switcher is turned on and off, there are high voltage pulses here. And these high voltage pulses, if there is a capacitance between this point and the secondary, you'll have a current, high frequency current going outside. It's called EMI, electromagnetic interference, and this is not desired. So you'd like to eliminate this. The way to eliminate it is, again, to wind this transformer. This is the high frequency transformer. This is going to be now a ferrite core, not a silicon steel core. And in this case, you'll connect the inner wire to the drain side, while the other side, this is the bus side, will be connected here, so that the high voltage pulses are buried inside here, and you have the capacitance between this bus side and the secondary. Okay, let's have a look at it here. We have eliminated this one by burying this wire inside, and then we have this part here. This is now between the bus and the output, and this is now the capacitance existing within this high frequency transformer. Now the question is, of course, what type of voltage do we expect to see here? Okay, this will be the voltage that will penetrate to the secondary. Okay, so let's have a look at it. Here we have this full wave rectifier. This is the line side. This is the neutral. Now again, there is an AC voltage between these two lines, but this line referred to ground is a potential of ground. Okay, so you might say that referred to ground, this is 0, and this goes to positive and negative. This is the situation. Now, we connect this AC to the bridge. So we have two phases, the positive and negative. And again, this point here is connected to the neutral side. So in one phase, you have this neutral side connected to the bus. This is the bus we are talking about. This is this bus here. So this will be the neutral potential, very close to ground. However, when we are at the other phase, this is now the neutral is here, and this is the hot side here, and you'll have a positive potential here. Okay? So, if we look at this bus, we see low, neutral, almost ground, and then high. So it looks something of this nature. This is the voltage here referred to neutral, okay? Not between these two, or not between these two. Between these two, there is a DC. Between these two, there is an AC. We are talking about the voltage here referred to the neutral. So we have a low frequency component on the bus referred to the neutral. Now suppose we flip now this plug. Will it make any difference? No, because if we flip it, the phases will be flipped, but again, we'll have this point here neutral, this point here neutral. So on this phase, this will be low, and on this phase, this will be high. So we'll have again the same situation here. What happens here now that we have eliminated this by burying this wire inside the core, but we have now this capacitance. We have a low frequency part here, and so therefore we're going to have the same situation as before. That is, if this is now, or these parts are now connected to the casing, and if it is the metal cases, when you touch it, you will feel this tingling sensation. Of course, the intensity of the sensation depends on the size of this capacitor. We assume, of course, that the adapter has passed the regulation, the code, and from safety point, the current will be low. That is below about 3 milliamp, so it's not dangerous. But even for much lower current, you will feel this electrical tingling sensation. How can we remedy this? Okay, one way would be to put a shield. Okay, a shield between the primary and secondary, and the function of this shield is actually to block the electric field between these two, that is to sort of eliminate the capacitance between the primary and secondary. Now the shield could be an extra winding with wires or foil. Actually, foil would be better. And this extra winding is connected only in one side. The other side is open. You don't connect anything to it. Okay? So it's in between the primary and secondary, and the way it's implemented is here we have it. This is the primary. This is now the shield. Okay? So it's wrapped around the primary. This part is not connected, while you connect only this part. The secondary is wound around this thing, so therefore the capacitance between the primary and secondary is very, very low, and therefore the current will be very low. Okay, so let's have a look how you connect it. This is now the shield, and the place to connect it to would be the neutral. So that here we have a sort of a plane, a metal cover of the primary, which has a potential of the neutral. This is now the capacitance between the neutral and the secondary. So referred to ground, there's no potential here, or very low potential, and you won't see, you won't feel anything when you touch the casing, the metal casing here. Okay, so this would be a way to remedy the problem. Now, what happens if you flip this plug, if you can flip it? Certainly in the European two-prong you can flip it, in the US, depending on the socket. In this case, you will feel the tingling, because if you flip it, then this becomes the hot part, and here we have now a metal part which has a capacitance to the secondary, and now it is hot. There's a high voltage on it, the line voltage on it, and obviously you'll feel the tingling, pretty much so. So if you use this idea, then you have to make sure that you plug it correctly. And the thing is that, of course, even in the European case, if you feel the tingling, you'll flip the plug, and then you don't feel the tingling. To support the theoretical presentation that I've given earlier, I did some measurements on a laptop that I've recently acquired. This is the surface of the keyboard, and this is here the surface that when you touch it, you feel the tingling. The manufacturer of this laptop is really not important, because just about all laptops have the same problem of touch feeling if there is a exposed metal part on the casing. So this is just a typical case, nothing special about this particular laptop. Now, the first measurement that I've done is just to look at the neutral. We have an oscilloscope here. This is the 3-pronged socket. This is the plug of the oscilloscope. Here is the probe, putting it to the neutral side. This side, the ground side, is open, but it is internally, of course, connected through here into the local ground. So the measurement is in fact between the neutral and ground. And what we see here is sort of a dirty signal in the area of 300, say half a volt, which is not so bad for a neutral line. Okay, so this is the neutral. And if I open it and look at a higher time resolution, 50 microseconds per division, I see here the spikes of this noise. Okay, there's nothing really special about this neutral. It's pretty good as compared to other places. So now the actual measurement. Here's the oscilloscope. Here's the probe. This is the laptop. This is the surface area that I'm feeling this tingling. And the probe is touching this area. The other side, the ground side of the probe, is open, not connected to anything, but it is internally, of course, connected to the local ground through the plug. So, in fact, this measurement is between the surface and the local ground. Now, the input impedance of this scope, with the probe, of course, is 10 megohm. Okay, it's a step-down attenuator type of a probe, very typical, and the total impedance, total resistance is 10 megohm. Now, what we see here is 50 hertz spikes. This is 50 hertz. And we see positive and negative. This is a result of the remnant signal due to the rectifier, the bridge rectifier of the converter. Now, we see here voltages up and down. This is when the diodes are conducting and the bus is reaching the input voltage. We see it plus minus and not like 0 and plus as I've shown before, because we are going through a capacitor and the DC level is of course filtered out, so we are left with the AC component, which is plus minus. Now the signal level is really not that much. It's only 240, 237 millivolts. That's what it is, peak to peak. And also we notice there is some high frequency ripple here, which is sort of superimposed on the signal. And in fact, we can have a look at it here. And this is the high frequency signal. Now, let's look here. This is 50 microseconds per division. And if I look at from this point, it is less than 50 microseconds. 50 microseconds is 20 kilohertz. So this is like, say, 25 kilohertz or something like that. I'll talk about this a little bit later. But the point is that what we are measuring with this probe here is this signal peak to peak of 237 millivolts. The question is, how good a contact is this? Now, this metal feels like aluminum. Well, it's kind of light, and I assume it is aluminum. Now, aluminum is known to be oxidized very easily when exposed to air, as a matter of fact. And this oxidized layer is non-conducting. Furthermore, perhaps the manufacturer actually anodized the surface to passivate it, to protect it even more. So this contact can be actually very poor. So first of all, let's see whether there is a conduction on the surface. So I've taken a ohmmeter, pressed the two leads here on the surface, and lo and behold, there's nothing here. It's many megohms, tens of megohms, so it's kind of an insulator here. And again, the reason is that we have the metal, this is the aluminum, we have the surface area covered with some insulation, oxide, the anodized surface, and therefore the current path is through actually capacitance. Okay, that's not galvanic conduction, it's a capacitive conduction for the AC component. So this is really what happens here. So in order to enhance the conduction and to see what's going on, I've taken a wire with strand, spread it out, and put a paper on it, and then cover it with the lid. Okay, this is the monitor here. Cover it out so it will press against the surface. And here what we got in this case. This is the oscilloscope again, and lo and behold, it's 9 volts. That's much higher. Okay, so we understand now that the probe just touching one point is really not getting a good conduction. So the strands are now making a much better capacitive contact to the surface. To increase even more the capacitive conduction, I've made some experiment with a digital voltmeter. Now here is the common lead, which is connected to the ground side of this outlet. Okay, this is the ground point. This is, by the way, the adapter of the laptop. Okay, it's a 2-prong adapter. And I put a butcher knife with a large area pressed against this surface, and then touched the other lid to the knife. And lo and behold, we have 60 volts. Okay, so this implies that the actual voltage that is down underneath this insulation is fairly high. It's probably even higher than 60 volts because we have a drop on this capacitance too, which is fairly large here because I have a much larger area and this is flat, again, flat areas, but still we have a fairly high voltage that's 60 volts. So what is really happening here is that we have this laptop now. This is the line, the hot side, the neutral side connected to it through the plug. And this is the internal impedance, which is low. We have this capacitor or capacitance at the high frequency transformer of the switcher, of the power supply, of the adapter. And then we have this capacitor. This represents this aluminum to the insulation layer and the voltmeter. So this is now the current that we've measured, and we have measured here 60 volts. Now back to the question of interferences. Now the laptop has been unplugged, and with the same arrangement of the spread wire strand, we measure the voltage, and we see again this high frequency component. There's very little AC now, but there's a high frequency component, same as we've seen it before, that the laptop is turned off. There's no operation of the internal inverter, either in the adapter or in the laptop itself. So this is probably coming from outside. And indeed, when it is like 20-25 kilohertz, it kind of resembles the frequency of fluorescent lamp ballast, electronic ballast of fluorescent lamps. So we turned off all the fluorescent lamps in the room, and indeed, this high frequency disappeared. Okay? So the high frequency component that we have seen has nothing to do with the operation of the laptop. It's coming from outside, from the lamp. And what is really happening here is that we have the lamp, which is fed from an electronic ballast. This is, let's say, 20-25 kilohertz. There's a capacitive, parasitic capacitance between here and the surface of the laptop through air. It could be very low, but then the impedances are very high here. So even a, say, 1 picofarad is sufficient to bring in some interference on the surface. Then we measure it with a 10 megohm oscilloscope, and we have in the room wires in the walls of 220 volts, and there's also capacitance between these and the laptop. So we have sort of a accumulation of interferences coming from all areas that we see here on the oscilloscope. Now, when we turn off this electronic ballast, then of course this contribution is disappeared, and we have only the 50 hertz. Now, if I put my hand on the laptop, I'll get this attenuation of the signal from here to here. Okay, so just putting my hand on the laptop. And the reason is that when I put my hand here, I'm adding another path to ground through the capacitance of the body, or the impedance of the body, I should say, in general. Usually it'll be capacitance because I'm standing on wearing shoes. And this is an extra attenuation to the signal coming from here. This one is off. So the signal coming from here, and due to this extra low impedance, then of course the signal here is becoming smaller. So I think we understand what is really going on. Some signal are coming from the laptop. Well, there's some interference which is coming from outside. Let's forget about them. That's not the issue of this presentation. Now let me do some basic calculation to see the current level, the voltages, etc. And I'm now concentrating on the knife experiment. In this knife experiment, we have 220 volts, an internal impedance which is low. We have the capacitance. This is of the high frequency transformer. This is the surface area. We measured here 60 volts with an ohmmeter, which has a 10 megohm internal resistance. So first of all, we see that the current that's been passing here is 6 microamp. That's it. Now, in order to do the calculation, I'm assuming that this capacitance, this knife capacitance, is higher than this one. So this could be considered a shortage compared to this one. And the same thing goes from this for this impedance, okay? This impedance is smaller than 1 over omega C, and this capacitor is larger than C. So we have a divider here between 220 and the voltage here. So we have Rm divided by the total impedance. This is the total impedance here, and is equal to 60 volts. So I work it out, and plugging in Rm 10 megohm, omega 2 pi 50, I found that this capacitance is 100 picofarad. So the internal capacitance is estimated to be approximately 100 picofarad. Now, if I touch here with a good connection, and the impedance will be small, usually the body impedance is smaller than 10 megohm, I can get up to, this is with RM0, this is like short here, get up to 7 microamp. So the thing is that this is very, very low as compared to the 3 milliamp of the safety standard, of the touch current safety standard. And we still feel it. So we can actually feel very, very low currents. Now, there is, however, a very strange phenomenon that I found, and I like to show here. When I did this experiment with the knife, I found that when I touch the knife with the finger, I don't feel anything. Nothing. No tingling, nothing at all. At the same time, with the same experiment, same setup, when I touch here, I do feel the tingling. I do feel the tingling. We know that there is sort of 60 volts underneath, and I feel the tingling when I touch here. I don't feel it here. Interesting. My explanation to this is for I didn't find any explanation, so I'm coming up with my own. Now, in the case of the surface of the laptop, we have a rough surface. This is the typical aluminum, sort of enlarged surface area, and it is insulated. And we sort of slide our fingers across it very lightly. We touch these points, and the current is flowing these points, and so that the concentration of the current is fairly high here, sufficient to excite some of the nerves that we have at the end of the fingers. So we feel it. If we press the finger on it and the surface area becomes large, we don't feel anything. So it is the concentration of the current in these points which makes this tingling feeling, touch feeling. Now, in the case of the knife, this area is conducting very good. Okay, it's stainless steel, no coverage, no insulation on it, and as we touch it, there is a large area, even lightly, there is a large area, so that the current density is very small because of the larger area, so we don't feel anything. So this will be my explanation to what is really happening here. So let's see what are the conclusions of this little study that I made. First of all, we found that a capacitively coupled voltage on the surface of a laptop, which is a parts which are of metal made, can approach 60 volt and probably higher. And this would be with a fairly small inter-winding capacitance of, say, 100 picofarad. Now, tingling sensation is apparently enhanced by an uneven insulated surface, which is capacitively connected to the metal surface. So as we slide our finger over these uneven points, we feel this tingling. And the most surprising thing is that this tingling is felt with currents as little as 5 microamps, very, very small current compared to the 3 milliamp limit of the safety standard. This actually brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it interesting and it will be useful to you in the future. Thank you very much.